So welcome back. This video is going to cover the general retention model for estimating customer lifetime value when you have a banger situation. So what I mean by that is customers join or enroll or subscribe or whatever, and they send you a subscription amount each month until they decide to end the relationship in a bang. So they cancel and it's done and they never come back ever. In the previous set of videos, we covered the simple retention model, which made a very big assumption, namely that the retention rate, the probability that a customer gets retained in any given period, does not depend on either the customer or the time period. Well, we're going to relax those assumptions in this general retention model. So let me start out with a little bit of notation. So as before, R sub t is the event that some customer, I could put customer I in here, and that's where we're going to be going next. But to keep our notation simple, let's forget the I for now. That some customer is retained in period t. And we're going to say R sub t is the probability of our event, big R sub t, occurring. Now, I'll just put in parentheses over here, the SRM implies that the probability of RT is equal to R for all values of t. Whereas now, we're going to give ourselves another subscript, is the way to think about this. So in order to describe the general retention model, we really need some concepts from survival analysis. In survival analysis, the survivor function is the probability that a customer cancels at time t or later. Or more generally, you could say that the event happens at time t or later. So the patient has survived at least up until time t. Maybe the patient dies right now, or maybe the patient survives longer. So we can write this as the probability that t happens at some time t or later. We're going to continue to assume independence, and therefore, in order to get this probability, we are simply going to multiply all the retention rates up through the previous period. So for example, what is the probability that a customer survives up until time period 3? Well, that customer would have had been retained at period 1 and at period 2, therefore I multiply those two. Now a useful recursive relationship is as follows. So what's the probability that I survive up until time period t? Well, it's really the probability that I survive up to time period t minus 1, and you survive another period. I survive at period t minus 1. That gives me s at t. I'm going to go over to my document camera, and I've made what I think is a really useful summary table. And why don't we just start dropping in these functions. So for the general retention model, this is going to be the product from period 1 to t minus 1, R sub t. But we can think of this as RT minus 1 times S at t minus 1. Now for the simple retention model, we didn't really write it out, but this is extremely easy to get at. This is just going to be R to the t minus 1 power. And so if all of these R sub t's are equal to the same number R, then notice I've just multiplied R by itself t minus 1 times. So that's the survival function. The next function that we care about is the probability mass function. Survival analysis, I'm going to say, probably deals with continuous functions more than discrete functions. And so often in software, this gets labeled the PDF. assuming a continuous density. But for our setting where we have these discrete payment periods, we're going to be using a probability mass function instead. Well, let me go write out what we derived in my previous video for the simple retention model. So I have to keep you around t-1 periods, then I lose you. So that would be the PMF for the simple retention model. For the general retention model, the basic principle is the same. I'm interested in what's the probability that you survive up until time period t-1, and then I have to lose you. So let's just go write this in. This is going to be S at t times 1 minus R sub t. Now, if we distribute S sub t, I end up with, well, 1 times S sub t is just S sub t, minus, well, S sub t times R sub t. Well, notice from our previous expression, this is just S sub t plus 1. So we can rewrite this as S sub t minus S at t minus 1. So I like to call this the unconditional probability of failure. So without conditioning on anything, if I just picked a customer at random, what's the probability they go away at time period t? We can see that that's just the difference in the survival times. So we can think of this as the slope of the survivor function multiplied by -1. You can really think about dividing this by 1. So for a 1 unit change in t, what is the change in the PMF? It's going to be the difference between these two. So this is just how we integrate the PMF to get to the CDF. CDF is just 1 minus the survival function. Maybe I should write that in here. This is 1 minus the CDF. If I take the derivative of the CDF, I would get the PDF, or PMF in this case, since we have discrete time. And so that's really what this is about. The next function that we need to know is called the hazard function. So the hazard function you can think of as giving you the probability of instantaneous failure if you have continuous distributions. If you've seen some survival analysis before, that was the way it was defined. Since we're using discrete time here, you can think of it as what's the probability that I fail or cancel in period t, month t, given that I've made it up to period t. So I think this makes it very clear. What's the probability I cancel now, given I haven't already canceled? So I like to call this the conditional probability of failure because you're assuming that the customer has survived up until time period t-1, and now you want to know what's the probability that they go away now. I'm going to denote this by the Greek letter pi. So pi sub t is going to be this conditional probability of failure. So if you remember, with conditional probabilities, you take the joint probability, divide by what was given, and so the probability that you survive up until, survive to time period t is just S at t. So I divide the PMF by the survivor function, and if I do that, okay, so let's go see what is this PMF. The PMF is sitting right here. The survivor function goes away, and we're left with just 1 minus the retention rate. So let's go fill this in. This is going to be 1 minus the retention rate at time period t. In the case of the SRM, it's just 1 minus the retention rate since they're all the same. Now, one thing that's important to notice about these is if I know one of these three functions, I can find the other two. So if I know the hazard rates, or the retention rates, so 1 minus the retention rate gives me the hazard rate, then clearly I can find the PMF or I can find the survival function. If I know the survival function, I can get to the PMF, right? I can just do this differencing. And so these three functions really describe the same problem, but they describe a different aspect of them. So if you know one, you can find the other two. So the next thing we did with the simple retention model was to find both the expected value of t as well as the lifetime value. So lifetime value is the expected present value of the future cash flows. So how are we going to do that? I'm going to define m sub t as the discounted cash flow that occurs at time period t, assuming the customer is active. So if the customer's already gone away, then m sub t is 0. I'm not interested in that. But if you do get a payment at time t, what is that worth to you? So clearly, lifetime value for a given number of months is going to be the sum of these m sub t. So the discounting is baked into the definition of my m sub t. So in order to find lifetime value, all I have to do is find, the expected value of this function of t. So how do we do that? Well, if you remember, the expected value of some function of a random variable is just that function of the random variable times the probability. What we have is just the PMF times that CLV function. Well, what is the CLV function? We've written that up here as the sum of the m sub I values. Now what I'm going to do is use the fact that addition is commutative. So if I take 1 plus 2, I get the same as 2 plus 1. And I'm going to rearrange the terms in this sum. So I'll multiply p sub t times the m, so bring that sum out in front, and rearrange terms. So what you'll see is we end up with p sub 1 times m naught, plus p sub 2 times m naught, p sub 3 times m naught, and so forth. Plus, p sub 2 times m1, p sub 3 times m2, and so forth. Now, what we notice is that if I add up the probabilities of a payment occurring at times 1, 2, and so forth, what we really have is the survivor function. So if I've survived up until time period 1, so I cancel at time period 1 or later, that's what this is after I pull the m naught out. And the second term here is just the survivor function at period 2. And so what we've just done is derived a slightly simpler version of how to compute this expected value of the CLV function. So let me go write this into our table. This was m times 1 plus d over 1 plus d minus r. In this case, we're going to say m sub t is whatever the payment is, if there's a common payment, 1 plus d raised to the t power. That's a d. You can't quite see that on my document camera. Then lifetime value is just going to be the sum t equals 1 to infinity, probability of t times the CLV for that. But what we just showed is that this is the sum s at t m t minus 1. So sometimes it's going to be easier for us to evaluate this expression than this expression. Now we can actually derive another result from this. If I want to count the number of periods that a customer is active, I'm going to let m sub t equal to 1 for all t. So every period counts as one period. Then the expected value of just t is going to be the sum of the survivor functions. So Let's go fill that in as well. The expected value of t for the simple retention model was just 1 over 1 minus r. For this, it's going to be the sum t equals 1 to infinity s at t. And that gives us the mean or expected number of periods that a customer is going to be active. So a couple more results. If I drop in the value 1 for m sub t, so every period counts once, and I assume the same retention rate for all periods, then we need to go find the sum of 1 times r to the t minus 1, which we recognize as a geometric series back in calculus. So let me just remind you the limit. If we let t go to infinity of s sub t, if we take the limit as t goes to infinity, I equals 1 to t, s sub I, this is a over 1 minus r, so that's the very famous formula that you get in your calculus class. In this case, a is 1, and of course 1 minus r is there. What falls out of this is one way to prove that the expected value of t is 1 over 1 minus r, as I claimed here. If I were to let m sub t equal just whatever the m is times divided by 1 plus d to the t, so that's what I wrote right here, we have another way to arrive at the sum for a simple retention model. So now I have a geometric series. This is my a. This is the r term. So if I take a over 1 minus r, we end up with the formula that we had before, m times 1 plus d minus r. Let's now do an example. Let's say that I have a cell phone provider. I know it's not realistic to have 6-month contracts, but let's use 6-month contracts rather than, say, 2-year contracts because it fits on one screen. So for pedagogical purposes, we'll use the 6-month period. In real life, you may have 24 periods and you have a few more rows, but the math is the same. It just wouldn't fit so easily on one screen. To keep our life simple, let's say that customers pay $50 at the beginning of each month for their cell phone service. Now, in my previous videos, I said that sometimes at the beginning of a relationship, the retention rates aren't as good. You can think of it as kind of a burn-in period with the customer. So let's say that in the first month, 80% are retained. Now in the second month, if I can get you past the first month, retention rates shoot up to 90%. And then retention rates are 95% thereafter unless you're out of contract. So remember, your contract ends at period 6. So you're out of contract in month 6, 12, 18, 24, and so forth. And so when you're out of contract, the retention rate drops to 50%. Where we're going to go with this in a minute is I'm going to make you pay a penalty if you want to cancel when you're not in contract. But let's take this one step at a time and not worry about a penalty just yet. Let's assume that we have a 1% discount rate. So I'd like to work this live. There was an optional video that showed how to do the simple retention model in Excel. If this example is not clear, you might want to go back and watch that other video because that one's a bit easier to understand than this one. All right, so I've set up a spreadsheet for us here. This is going to be the observed period of cancellation, and I've already written in my m sub t. So m sub t, remember, is the present value of the payment that you're going to get at time period t. if I get $50 a month for this service, I'm going to discount that back to time period 0. So this is time 0 is when I take out the cell phone plan. You're going to see that's worth $50. If you can retain me in my first month, then I'm going to give you another $50 1 month from now. And that $50 is really worth $49.50 to you right now. So that's the present value of the promise of $50 1 month from now. Likewise, if you keep me for the second month, then you'd get $50 2 months into my relationship. That has a present value of $49.01. Well, let's go fill in the retention rates. I think we said the retention rate for the first month was 80%, then 90%, then it was 95%, except when it's a multiple of 6. An easy way to fill this in was with an if statement. So if I take mod my month number, comma 6, and if that equals 0, then the retention rate is going to be 0.5. Otherwise, the retention rate is 95%. So let's see if I did this right. All right, great, I think I did. If I copy it down, you're going to see month 6, a lot of customers go away. Month 12, more customers go away. Otherwise, the retention rates aren't that bad. Well, let's go find my other functions. So the first one is the survivor function. An important question is, what is S at 1? So what's the probability that I survive until period 1? So in other words, I cancel at time period 1 or later. So I've survived up until the end of the first month. Well, let me just state that that is equal to 1. So 100% of your customers will survive up until the end of the first period, and then some of them get retained, some of them you lose. All right, now thereafter, we're going to take the previous value and multiply it by the retention rate. So how many customers survive up until the end of month 2? Well, the answer is 80% of them do. How many customers survive up until the end of period 3? Well, you're going to keep 90% of the 80% who are still around, so 72%, and so forth. All right, so now we have our survivor function. The survivor function, if we did stuff right, should go to 0. And so when we go down here, we can see it's approaching 0. I think we did it right. All right, now it's time to compute the PMF. And so remember, you can think of the PMF as like negative the derivative of the survivor function. And so the derivative is just going to be the difference divided by 1. So let's go work that out. So the change in the survivor function is going to be S sub 1 minus S sub 2. I'm keeping a running total up here. If I do this right, the PMF, since it's a probability mass function, had better sum to 1. So let's go see if that's the case. So I'll go copy this down, and lo and behold, it sums to 1. Let's just think through the interpretation of one of these numbers. So what is 3.6%? So that's the unconditional probability that a customer cancels in period 3. So it's not the hazard, it's the unconditional probability. So if I just pick a customer at random and I ask you what's the probability this customer is going to go away in period 3, the answer is going to be 3.6%. Contrast that with the hazard. So the hazard is going to be 5%. So if I make it to the end of period 2, the chance that you lose me in the next period is going to be 1 minus the retention rate. So it's very important to keep the hazard / retention rate separate from the PMF. So this is the conditional probability that I lose you, given that you've survived. This is the unconditional probability. Let's now compute lifetime value. And what I'd like for you to remember is that we had 2 ways of doing this. So one approach is, call this the shortcut approach, is we just take whatever payment that I had in the previous period times the chance that you've survived up until that period. So if I take the survivor function times the present value of the payment that I got at time t minus 1, okay, so with certainty, I'm going to get $50 from you. I'll copy this down, and what we end up with is the lifetime value of a customer in this complicated situation is about $340. Well, an alternative way to do this is to first look at what is the lifetime value if I know your cancellation time. If you cancel in period 1, you're worth $50 to me. You gave me $50 at the start of the relationship at time 0, and that's all I get from you. If you cancel in period 2, what are you worth? Well, you're worth what the $50 plus I get another payment. A customer that cancels in period 2 is worth about $99.50 right now. So this is the present value of all those payments. If I copy this down, someone who goes away in period 3 is worth a little bit under $150. All right, so a different way of computing lifetime value is going to be to compute this, whatever you're worth, if I know t, weighted by the likelihood of that happening. So let's go do that. I'm going to go take the PMF times this value. So with probability 0.2, I get $50 out of the relationship. With probability 0.08, I get $99.50. And let's just keep doing that, and lo and behold, we get the same number, which all I've shown is that this messy expression works, that's exactly what I said it was. So another question we might ask is, what's the expected value of t? And if you remember from my lecture notes, that's just the sum of the survivor functions. So let's go figure this out. I'm going to say the expected value of t is equal to the sum, oops. So if I go find the sum of these survivor functions, what this says is I would expect to keep you about 7 months. And so I always think of this as a really simple way of getting at lifetime value. If I keep you about 7 months and you're worth $50 a period, that doesn't account for the discounting, of course, but you're worth about $350. Well, a more precise number would be $337, but that mean gets me in the ballpark. So if we go back to the course packet, I hate the graphics in Excel. I've graphed these functions. These are the types of functions that you're going to get from good survival analysis software. So survival analysis software will provide you with the hazard function, and here's our hazard function. At period 1, there's a 20% chance I lose you. Period 2, there's a 10% chance. Thereafter, there's a 5% chance I lose you unless it's a multiple of 6 when you're out of contract, and then there's a 50% chance that I lose you. So what you should notice about this is the conditional probabilities are all at 50% versus the PMF. So here's the PMF. Think of these as the unconditional probabilities of failures. And so these spikes decrease. And the reason for that is because there aren't many customers left. Unconditionally, there are just not a lot of customers who are going to survive up until time period 30. So the conditional probability of losing a customer at time period 30, if that customer survives until period 29, is 95%. But the probability of losing someone at period 30 without knowing they made it up to this time period is quite small because chances are that customer's already gone away. Here's the survivor function. So the survivor function you're going to see takes a dramatic drop every 6 months. Otherwise, it takes a small step down every period. Well, let's make the example a little bit more complicated now. Suppose that this customer has to pay a $100 penalty if they cancel when they're in contract. So I'm out of contract at 6, 12, 18, and 24. I can cancel without any penalty. Otherwise, I have to give you an additional $100 to get out of my contract. So what's my lifetime value now? This is very important. I cannot use this formula. The reason for this is m sub t depends on t. So, in other words, if I cancel in period 6, then the amount of money you get from me in period 5 is going to be $50 discounted back to the day. But if I cancel in period 5, the amount of money you get from me in period 5 is, well, whatever the $50 plus $100 discounted back to the day. So this m sub t is going to change, and that complicates our life. So in order to solve this problem, we're going to have to go back to the basic definition. So let's go do that. I'm going to go over to my Excel spreadsheet for a second, and I've added a new column that I've labeled the penalty given the time that you cancel. So if I know when you cancel, what is that penalty? Let's go think about this. I'm going to put in my mod statement. So if A5 mod 6 is equal to 0. So the way to think about this is equal to 0 whenever I cancel in period 6, 12, 24, 18. So I'm out of contract. Then the penalty is 0. You don't get anything from me. However, if I cancel out of contract, you're going to get $100 from me, but it's discounted back to that time period. And so if I cancel in time period 1, the penalty part of my value is just under $99. So let's go copy this down and see if it works. And I think it does. So if I cancel in period 6, the penalty part is 0. Otherwise, you're getting $100 from me at some point in the future. Present value of that diminishes the longer I remain a customer. So what's CLV? Well, this is going to be the probability of t times whatever the value is. So what's the value? Well, you're going to get something from the payments plus something from the penalty. So I just add those up, multiply it by the probability. And if I copy this down, I should be getting a number that's a little bit more than $137. It shouldn't be more than $437. But it should be, I'm going to guess a bit more than this. So let's go see what happens. So it looks like the lifetime value goes up by about $50 or so if we have this penalty with it.